Today we have Dima Zakharov as a speaker. He needs, I guess, little to no introduction, but I'll still make some small introduction. So he's now at MIT and last year became the youngest recipient of the European Prize in Combinatorics. He'll talk about his work with Alex Cohen on moderate doubling sets. Welcome, Dima.
Yeah, thanks, Andrei. Thanks for inviting me. So, it's a pleasure to be back, at least remotely. I'll talk about additive combinatorics. So here's the setup. So let's say we have a group G, which will be a abelian group. And I'll mostly think about two examples. So either you can think of G just being the set of integers, or fp to the n for some prime p. So these are like the main examples. And let's say we have a set A inside of G, which is a finite set. And we are interested in the subset so we really like to understand A plus A. So this is the set of A plus B with A and B in A. And the main question in additive combinatorics is so if A plus A is small, then what can you say about A? Basically, you want to say that A has to have some sort of structure. It's a very classical question, and like our main, we were thinking about kind of moderate doubling regime of this question, which I'll get to. But I just want to kind of recap some basic known results. So the classical result is Feynman's theorem. So it says that if A plus A is very small, then A has to kind of resemble a subgroup or arithmetic progression. So I guess you can think of this kind of subject is study of like approximate subgroups. So if A plus A is small, then A is approximately subgroup, and you want to make this heuristic kind of precise. So here's the result. Let's say we know that A plus A is at most k times A for some kind of constant or parameter k. So it's not hard to see that A plus A cannot be smaller than the size of A. So we always know that it's at least A. And so suppose that it's within this lower bound up to some constant factor. So then Feynman proved that then A is essentially an arithmetic progression. So then there exists generalized arithmetic progression P. So it's a set of the form sum di ni where D1, so let's say from 1 to R, D1, dr fixed, and N1, and Ni like range from, let's say, from 1 to some capital Ni. So it's a R-dimensional arithmetic progression such that so A is contained in a BCO of 1 translates of this progression, and the rank of P is also bounded, and the size of P is linear in A. So basically you can find a general arithmetic progression of comparable size. Sorry?
This is the statement for Z, right?
Yeah, so you can think of A and Z.
Meaning for
if
FP,
A is a subset, yeah, if A is a subset in Fp to the n, then you replace P by then P is a subspace. Yeah, so over Z, we think of generalized arithmetic progressions over Fp to the n. Let me, I guess, say it a bit more precisely. So this is just for Z. And if A is a subset in Fp to the n, then the same statement holds when you replace P with just an arbitrary subspace V in Fp to the n of comparable size to A. V.
Dima, another question. So rank,
Yeah.
it's just R, or you want to say some kind of something else for the Z case? So
Sorry?
rank P is equal to OK.
Yeah, that's just R.
I mean, just R, right?
Yeah. That's like how many generators it has. Yeah.
Yeah.
Okay. Yeah, and the version of RFP was extended from Feynman's theorem by Green and Rouja. Something like O5. And Feynman's theorem is from ancient times. I think it's 70s.
And in this generalized progression, is it injective? So this
Yeah.
some should be distinct. Yes.
Yeah. It doesn't really matter. So if there are like overlaps, then you can kind of replace it by a slightly different progression without overlaps. So, but yeah, you can think of distinct. Yeah, I will not be focused on Z that much, but this is kind of the very classical statement. Yeah, and over Fp, I should say that P is a kind of fixed, and N is large. So that's kind of the range I'm thinking about. Yeah, over Fp, the progressions get replaced by subspaces. So V has size big O of K A, and A is a subset in O of 1 translates. Okay, so these are classical results, and okay. An important question about this result is the quantitative dependence on K. So how of K depends on K in these results. So for constant K, we kind of know what's going on, but what if K gets kind of large? So what can we say then? What can we say? So there is a conjecture that basically all dependencies should be polynomial. So this usually called polynomial Freiman-Ruger. That basically of k should be just k to some constant c. I will not state it precisely, but I'll state the finite field version precisely a bit later. So that's kind of a big problem in the area, and recently there has been some remarkable progress. So in 2023, in a paper of, that's not alphabetical order, but whatever. So it's Green, Gowers, Manners, and Tao. So they proved this conjecture over F2. So let me tell you what they proved. So they proved this kind of Feynman's theorem with polynomial bounds over F2 to the n. So the result says that, so let A in F2 to the n be a subset such that A plus A is at most k times A. So then there exists subspace V in F2 to the n such that A intersect with the actually let me write it in the same way as I was writing the previous statements. So A is contained in because k to the c translates of V, and V has size at most A. And here C is a constant. And this is a pretty good description. So if you kind of, so you know that like if you have a subset, just a subspace V, then V plus V is V, so the size of the subset kind of doesn't grow at all. And so if you kind of mess it up a little bit, so you can take, instead of one subspace, a union of a few translates of it, and you can also like take rather dense subsets inside of each translate, then that thing will not expand that much either. And so this theorem says that that's basically the only thing you can do up to some.
Is it clear what C should be?
It's not that obvious. So
This case,
can
it be bigger like than 2?
So we know that C is at most 9. So they got 12, but it got improved to 9 by like some optimizations. And there is a construction showing that C should be at least 1.2. Basically, it's a bit silly kind of construction. You basically take one subspace and you like perturb it a little bit. So like maybe take one subspace and add a little bit of points in the one translate of it. And then you kind of play around with density and you check how much, what is K, and like you need at least 2 things to cover this thing, but like K will be quite small. So
Okay.
So some small examples show that like C cannot be like literally 1. Yeah, but it's some reasonable number. Okay, so this is a very nice result, and it will come up in a later discussion. So let me just tell you what happened after. So a year later, the same group, so they extended their proof to the case of FP. So kind of the same statement, but the constant C is now a function of P, which is like grows like P cubed. So for every fixed P, you get kind of polynomial dependence, but it gets worse with larger P. But the conjecture is roughly speaking saying that it shouldn't really depend on P. But it's still very nice progress. And another result which came out last year was by Agavan. So it addressed the case of integers. So he didn't quite solve the conjecture, but he got pretty close. So near polynomial bounds or Freiman. So roughly speaking, he showed that if you have a plus a is at most k times a, then the progression p that you get has size at most, so it'll be a, and there'll be some factor depending on k, which is like k to something slowly growing. So it will be like log k. And I'm afraid there is another factor. So it's something like this. So it's not polynomial, but like k is raised to like log k, which is pretty close. And it sort of used similar method. On the other hand, there are still some barriers to getting polynomial over Z. But this is kind of the state of art on this question. But what we will ask is slightly different. So let's say G is F2 to the N, and so PFR in particular implies that if A plus A is at most, let's say, 1.1, like A to the 1.1, then A has a kind of large intersection with the subspace. So with the translate. So this is like at least A to the 0.1. So
and you mean here V of the same size?
Yeah, for some V in F2 to the N with size at most A, and A is just some element of A. So kind of this is weaker than the statement, but this is kind of the basic corollary that you get, that the A cannot be like randomly placed inside of large space. It kind of has some amount of elements in a small subspace. But like this 1.1 is kind of the constant which pops out of the proof. So what about if B no less? So let's say A plus A is kind of just a little bit smaller than maximum. So we always have A plus A at most a squared, because it's a sum of like quadratically many things. So, and in the worst case, they just don't collide at all. And so what if we have like a little bit of saving over that? So in this case, PFR doesn't apply. And even if you had the most optimistic bound in PFR, so even best possible C is at least 1.2, as I mentioned before. So this fact that C is kind of separated from M tells you that you can't really say much about A in this situation. Like here you have this doubling constant K of order A to the 0.9. So like K to the C is larger than A. So this is kind of useless. And so kind of our question is, so first of all, we call this kind of moderate doubling. So this is and our question is, what can be said about A in this situation? So A is necessarily less structured because we kind of have a weaker assumption, but there still should be something. And so let me tell you what we can do. So this is a result with Alex Cohen. 25 minutes. So suppose that, so we only think about f2 to the n. So suppose that a plus a is at most a to the 2 minus eta or some a to the greater than 0. Like you can think of 0.1. So then we show that a has to intersect with the subspace quite a bit. Then there exists the subspace V, which is not too large. So it's at most a to some constant. And it intersects, and its translate intersects with A quite a bit. Okay, so let me tell you the quantifiers. So for any epsilon greater than 0, there exists some L greater than 0 such that this holds. So, like, for example, if you think of eta being 0.1, you can take epsilon to be 0.01. And so you get that A intersects with the subspace in at least 0.1, I guess 0.09 elements, and V is still polynomial. So A to the L, where L is just constant depending on this epsilon parameter.
L depends only on epsilon or on eta?
Yeah, it only depends on epsilon. Yeah. But kind of epsilon has to be smaller than eta for the result to be interesting.
And the result is valid only for F2?
Yeah.
Okay.
And
And
think
like if you drop, sorry, if you drop L, it's unclear if it's true or not, or is it not?
it's you mean like V at most A?
V at most A. Let's say we only care about small etas.
Yeah.
So because this example that you mentioned with K, right, it's something on the other side of the spectrum, right? It's not like for every size.
Yeah. Yeah, so in the
It
previous
might
theorem,
be
V was at most A in size. So it might be true with V equals A, but so I'll show you some examples which show that you should really think of V being quite large.
okay.
So examples. So basically, I have three types of examples. First two we kind of already saw. So let's say V is a subspace size. Okay, let me put this this way. So let's say we pick some V inside of f2 to the n and let A inside of V be uniformly random subset. Subset of size A. And we will choose how large we want V to be. So, and let's say that A is at least V to 1/2. So then, if I look at A plus A, then it sort of fills out V kind of uniformly. So A plus A will be basically all of V, and so A plus A is at most V, and so and I want to make this to be A to the 2 minus eta, so that means that V is A to the, okay, I guess I already wrote this. So here the subspace inside of which A kind of distributes well has size almost A squared. And so if you take kind of a subset of size the same as A inside, so if I take inside of V prime is A, then I guess this will still be somewhat large. Yes, I guess in this example that's okay. Like it's allowed to be the same size of A, but kind of the natural choice of V is this one, the one which contains all interactions. Okay, so this is kind of the random example. So here's another example. Let's say we again pick V inside of f2 to the n, and let A to be a union of random translates of V. So let's say it's V plus u1 plus u. Bar u1 m random. So they're just random elements in n of 2 to the n. So we will have that A has size v times m, and A plus A. So how large is A plus A? Well, it's going to be also a union of cosets. So it's a union of translates of V. So it's going to be kind of V plus, it's going to be the union of V plus uj, ui plus uj over all I and j. And so this tells us that A plus A is at most m squared V. And so we want this to be a to the minus eta. And so this works out to be that m is a to the 1 minus eta, and v is a to the eta. So in this case, it kind of turns out that this subspace V that we want to choose is actually smaller than A. So it has size a to the eta, because so A kind of interacts with each translate, but you can't really find a larger space which kind of captures more mass of A, because it's kind of random. It's a random translate, so they don't concentrate anywhere.
So this
that's
L can be kind of smaller than 1.
Yeah. So there is like a little bit delicate dependence between epsilon and L. So so our theorem doesn't capture like everything that can happen, definitely. Okay, so that's also kind of pretty simple example. So let me look at the third example, which is kind of the most interesting one. So let's say let's take A to be the Hamming ball. So I will choose A to be and choose P times N for some P between 0 and 1/2. So this is the set of vectors. So I view this as a subset in F2 to the N. So it's a set of vectors with number of xi equals 1 being P times N. Okay. So what do we have now? So the size of A will be roughly 2 to the n times entropy function of P. So where h of P is minus P log P is P minus P. And what about A plus A? So let me be a little bit crude, and let me just say that it's contained in n choose 2pn. And so what this gives you is that A plus A is going to be at most 2 to the minus You get it, right?
Y minus.
So I want to write it this way. So it's a squared over 2 to the pn, roughly speaking. And basically, the reason for this is that when you take the sum of two things, the elements, then it will be just two sets. Then their sum will be essentially 2pn. There will be some overlap, but it's a smaller effect. And basically, you get a subset of size 2pn, and you can get this subset in 2 to the 2pn different ways. Okay, so I made a mistake, so it should be 2. Let me write 2pn, and then there's some small thing. So basically, you have a subset of size 2pn, and you split it in two parts, in two equal parts. And this gives you the composition. And so basically, you sum two elements of A, and this sum is represented as a sum of two elements of A in at least 2 to the 2pn different ways. And so by kind of double counting, this gives you this. So there is like compressing of that size. Or you can just write down binomial coefficients and you can get the same thing. Or
entropy.
Sorry?
Or entropy.
Yeah, or you can compute some entropies. Yeah. Okay, so, and basically, if you want this to be a to the minus eta, then we get so let's say p is kind of small, so like smallish constant, then you will get eta of order 1 over log p. Basically, the size of A is like 2 to the n p log p, and here we have p like np, so there is another factor of log p which is missing. So eta will be 1 over log p, and so and our space V should just be everything in this case. You can take it a bit smaller, but to kind of to capture A, you really just need to take the whole space. And so you'll get that the size of V, so this is 2 to the n, so this is like the size of A to the 1 over entropy of P. And so if you want this to be L, so this tells you that L is 1 over h of P. And this is roughly 2 to the 1 over eta. So I'm thinking of entropy being roughly P to the minus 1. I don't care about the log even here. And so this gives you exponential dependence, eta. And let's say we like take epsilon to be roughly of the same size as eta. So L is at least 2 to the 1 over epsilon in the theorem. So this is kind of the main bottleneck.
But for this example, it looks like so for For L equals 1, you cannot say anything, you're saying, basically?
So for L equals 1, you can say something. So let's say L equals 1. I can choose a smaller subspace. So I can choose V to be like F2 to the some M times 0 inside of F2 to the N. And so V intersect A will be M choose PM.
PM.
So it will be, oh, you're saying it's going to be PM. Yeah.
Yeah.
Yeah. Okay, this is too hard for me.
But okay, so it will be something that is
Yeah.
non-trivial, right?
Yeah. Yeah. Yeah, I think you can make like V of the same size as A, and this will give you something, but it will be quite a bit smaller than like.
Okay, but kind of there is still but okay, so there the point is that there was the same eta kind of input.
Yeah, so here we got the intersection to be A to the eta minus a little bit. And this dependence is actually sharp on the second example. So you cannot make, so here A intersect V is A to the eta. In the second example, where you take the union of cosets. And so in this example, you can't make it larger, no matter how large L you take. So that kind
And
of
the
tells
third
you.
example with L equals to 1, it would not give the same eta, right? It would be
Yeah, I mean, I need to compute. It will give something. I'm not sure if it's larger or smaller than 8. I think smaller.
Yeah,
Actually, I don't know.
Small.
But yeah, there is some trade-off. So I think like there is potential to get some slightly better dependence between these parameters, but like at the moment we don't know how to do that. Okay, so but these are like basic examples, and so there are 3 examples: random subset, union of cosets, and like Hamming ball. And I don't know anything else, which is like substantially different. So these are kind of all examples I know. And based on this, like with the caveat that you can kind of combine these examples. So you can take, for example, this last example, take a random subset inside of it, take a union of some translates of it, something like that. And so based on this, you can pose many questions. And I'll pause some of them later if I have time. Okay. So let me tell you something about the proof. So the proof. Ideas. And so one of the main ideas of the proof is to work with entropies. So use entropy. And so all that we are doing is kind of based on the kind of tools developed by Green-Gowers, Manners-Tao. So in this paper, which resolved PFR over F2, so all of these results use kind of entropic techniques. And so we also do that. And I'll get to explain like why entropy like is useful in this context. So first of all, let me remind you some basic things about entropy. So if we have x, which is a random variable, so for us, we'll be looking at random variables on the group G. Then entropy of x is the sum of minus pi log pi, where like pi is the distribution of x. And a good way to think about it is that entropy is the expectation where x sampled from x of the log of the probability x is equal to x. So you sample a random point and you kind of ask how large is the log of the probability at a typical point. So it's a measure of the size of the variable. So in particular, you can think of variables which are just uniformly distributed over some subset. So if you have A inside of G, which is a finite set, then I'll denote UA be a uniformly random variable on A. So then the entropy of UA is just the log of the size of A. So this is pretty straightforward from this definition, because probability that x is equal to A is 1 over A pointwise. And so you just take in the log of that and average. Okay, so if you had a set, you can take a random variable, and then entropy is the same thing as the size. So nothing kind of happened, but the nice thing is happens when we take some sets. So if x, y are independent random variables, then we can think of their sum, so x plus y. And so, and this is the analog, like taking a plus b. So instead of the size of a plus a, we want to measure the entropy of x plus y, where x, y are uniformly distributed variables on A. So kind of A plus A is a slightly crude metric. Like it doesn't care if like some element appears lots and lots of times as a sum of two things from A or like only once. It's kind of measured with the same weight, but entropy kind of smooths that out a bit more. And so it turns out to be a nicer object. So note, so if I have x and y like this, then x plus y is supported on a plus a. And so the entropy of x plus y will always be at most log of the size of a plus a. So the uniform distribution always maximizes the entropy. If you haven't seen this before, then it's just application of Janssen. Okay. And so basically the plan is to study our problem, but replace everything with entropies. It might be not obvious
Just a small
from the
question.
start.
The things that you stated about this, so the result of Green-Gowers, etc.
Manner-style.
Now, so it also holds for the entropy?
Yeah. So I'll state the result now. Yeah. Yeah, let me state the result. So this is what they actually prove. So let xy be independent random variables on f2 to the n, and suppose that the entropy of x plus y is at most okay 1/2 entropy of x plus entropy of y plus let's say plus k. So you should think of x, y being uniformly distributed on the same set A. They don't have to have the same distribution, but that's kind of the main example. And then this 1/2 h of x plus h of y is just like A. So that's the size of the variables. So it's like h of x. But if they have like different entropies, then you just average the size. And then there is some like error parameter k, which is like roughly the log of the capital K from before. So if I have two variables like this, then there exists a subspace V subspace such that the uniform distribution on V has entropy at most this average, and I want to say that x and y are contained in a small number of translates. So how can I capture that? So one way to phrase this is to say that when I take x and add uv to it, so I like add a random element of v to x, then I basically get a random element in one of the cosets covering x. So I want to say that that guy doesn't increase too much. So entropy of x plus uv is at most entropy of x plus some constant times k. The same thing about y. H of y. So you can have this like picture in your mind that you have some x somewhere, and let's say this is your v, and then x plus v will be basically random variable supported on this kind of union of cosets with some distribution of how much each coset is occupied by x. Yeah. So that's what they did. Okay. And it's convenient to there are several equivalent ways to kind of write inequalities like this. So I find it useful to think about it in slightly different terms. So if I have a subspace V, so given V inside of the F2 to the N, I can look at the projection map. So pi V from G to G mod V. So this is the quotient map. And then I can think of the variable pi V of X. So it's basically so this vertical line will be kind of G mod V, and I can project my X onto this quotient. And so then I can think of entropy of the projection. And so if you kind of expand definitions, then the entropy of the projections, of the projection, it really is just entropy of X plus UV minus, okay, I'm gonna mess this up. Let's see. Okay, let me see if that's correct. No, it's not correct.
Should be UV in any case, right?
Yeah. Okay, let's see. I think this one is okay. So basically, pi V of X is just telling you which fiber I'm sitting in. So which translate of V I'm sitting in. And entropy of UV tells you what point inside of this fiber I'm at. And when you combine these two pieces of information, you recover X plus UV. And so equivalent way to state this is that the entropy of pi V of X is at most C times K. So I can mod out by a small subspace and kill off most of entropy of X. And like,
I'm a bit confused about this. So I think the greater than or equal, it's clear, right? So that if you move h of uv on the left, then the right hand side you can recover from the two left hand sides. It's like entropy of vector consistent of x and y is at most entropy of x plus entropy of y.
yeah.
But why is it equality? So you use the fact that like yeah. Yeah, I don't know. So is it yeah.
Okay, let me see a good explanation. Okay, so I think so let's take left-hand side and let's write it as pi of x plus uv. So I can do this because uv projects to 0, so it doesn't change anything. And now this I can write as entropy of x plus uv minus entropy of uv, right? Because like this variable is obviously uniformly distributed on every coset, and so
so you're using so you're using uniform distribution of this.
Yeah, so this variable is uniformly distributed on translates. So this is like
this is the key.
So this is like easy if you expand definitions, but yeah, you might need to think about it a little bit. Okay. So so basically, the goal is to find a subspace which modding out by pitch kills off a lot of entropy. And if you think of it as like in set theoretic terms, then if X is covered by few translates of a subspace, then if I mod it out, then I'll get just small projection. And small projection has small entropy. So it all makes sense. Okay. So now I can state our theorem in the same form. So this is so let's say X and Y are random variables on G as before, and entropy of X plus Y is at most entropy so let me write it this way. I minus eta entropy of X and Y. This will be like slightly different eta. It will be up to a factor of 2. Again, they should be independent. So basically, entropy of the sum is a bit smaller than total entropy of X and Y. So then there exists a subspace V such that there are several ways to write this. So I want to think of intersection. So in the set theoretic terms, we had translates of V intersect my set A a lot. So in this notation, I want to write it the following way. So if I take projection along V of X and look at the conditional entropy, so kind of how much information do I lose by projecting? So this is by definition is just this difference. So it measures how much entropy drops by projecting by V. And you can show that it drops by what it's supposed to.
You mean
So-
at most?
So I want to say that intersection is large with cosets. So so this thing will be large, but we will rewrite it in the alternative form in a second. So this will be okay. So basically, like here we had h of x. So this is equal to h of x plus h of y minus eta this guy. So this is kind of the deficit. And here we can write the same guy. So this is like a to the 2 eta, basically. So it's the same numerology as before, but in entropy is just a bit more convenient to use it like that. Maybe I should. In my notes, I wrote it differently. Anyway, okay, let's stick to this. Okay, and entropy of UV is at most L times entropy of X and Y as before. So for every epsilon, there exists L. So let me just kind of explain the meaning of this conditional entropy in the original setting. So if let's say X and Y are uniformly distributed over A, then what is this H of X, phi of X? So I claim that this is the expectation over X sampled from X of the log of the size of A intersect with B plus X. So I have some set A. I have some projection phi of V. I sample an element from A, like uniformly from A, and I measure how large is this fiber of this projection. So like it's X. V plus X is kind of the same thing as like pi V inverse of pi V X. So this is just what you get if you like write down the definition. So basically, what our result says is a bit stronger than like the first theorem that I wrote. It says that not only your A intersects some translate of A, but kind of it typically intersects it a lot in this kind of precise sense. So log of the intersection is usually at least like eta log, depending on normalization. Okay. So that's the entropic statement. Okay. So now I want to go on and explain the main reason why entropy is useful here. So this is something that's called fibering inequality. So here's a actually, let me just give one definition. So so let's say we have x and y random variables. Then I'll define the following quantity. I'll say S of xy is entropy of x plus entropy of y minus entropy of x plus y. So this is all this doubling mass. So this is the same quantity which kind of appears in the theorem. So we are saying that entropy of x plus y drops by some amount compared to the maximum possible value, and S of xy is this amount. This is non-negative. So basically, we want to keep track of what happens to this S of x and y. And so there is a useful inequality. So let's say I have xy, independent random variables, and I have a projection, or like I have a linear map from G to H, which is a linear map to some other group. So then we have the following inequality. S of x and y is at most let me make sure the sign is correct. Yeah, it should be right. Basically, whenever you have a projection, you can kind of split your variables into the projection and the fiber. And this move is kind of, you don't lose by doing this move. So this is at most S of projection of x and projection of y plus S of the fiber of x and the fiber of y.
So here it's p pi or
yeah. Oh, you're saying yeah, right. There's no v. Yeah, pi of y. So basically, you have some x here. So you have its projection. So this is pi of x. And you have fibers. And I'm saying that you can split x into its projection and kind of typical fiber. So there's some notation which I haven't explained. So there's a notation. So S of So this thing is by definition means that I take the average over, let's say, V sampled from pi of x and W sampled from pi of y. As of x conditioned on pi of x equal V, y conditioned on pi of y equal W. So you sample typical elements in the projection, and you condition on the projection being that. And then you average over all. So in this entropy calculus, this is a very convenient abbreviation where whenever you are conditioning by a random variable, you really mean by like averaging over all conditionings. Okay, so that's the inequality, and I think we can even prove it. So the proof is not difficult. So basically, I'll just expand everything. So xy is entropy of x plus entropy of y minus entropy of x plus y. That's just definition. Entropy, so for the projections, these will be just pi of x, pi of y, minus entropy of the sum. And for the fiber, it will be the same type of thing. So there'll be entropy of x conditioned on pi of x plus entropy of y conditioned on pi of y minus entropy of the sum x plus y conditioned on. So here I should be kind of careful what I'm conditioning on. It will be conditioned on pi of x and pi of y. So I'm taking the sum of these two creatures. So, and they're independent. So here it's important that x and y are independent. And their sum is distributed the same as this. And so, okay, this is quite nice because if I take a sum of these two, then by the chain rule, I just get this. The sum of these two is just this. And here I need to be just a tiny little bit more careful. So if I look at entropy of x plus y conditioned on pi of x and pi of y, then I can forget some information in the conditioning. So I will condition on less information, which will increase my entropy. So this is at most entropy of h of x plus y conditioned on pi of x plus y. So here I'm using the submodularity or like information processing. If you expand it, it's some simple inequality on entropies, but yeah, that's kind of how you should think about it. And now this quantity is exactly entropy of x plus y minus entropy of the projection. And so when you plug this in, you will get inequality. You'll get inequality in one of the two directions, and then you'll need to check the sign to check that it's in this direction. Okay. So this is a very simple inequality, but it's very useful. So here is the kind of proof kind of strategy, or like proof plan of the theorem. And this inequality was introduced by Green-Gauss, Meiners-Tau. So let's say we start with some xy with s of xy at least eta h of xy, and we want to show that there exists some v which interacts with x and y. So like projecting by v drops the entropy. And so here's how we can use the fibering inequality. So basically, let us cook up some projection map. So let pi from g times g to g be the addition map. Y goes to x plus y. And let's consider variables and consider random variables. So let's say x1, x2, y1, y2. So x1 and x2 are going to be copies of x, and y1, y2 are copies of y, and everything is independent. And then we will look at the pairs x1, x2, y1, y2. So this will be my new random variables, and their projection is the sum and I will apply fibering inequality to this. So on one hand, if I look at S of this x tilde, y tilde, then what we did, we just doubled our variables. So this is going to be just twice S of xy, kind of by definition. So it splits coordinate-wise into two terms. And on the other hand, we know that this is either at least or at most, hopefully at most, as of the projection plus the fiber. Okay, so this guy is just the sum set of x versus the sum set of y. And this is just conditioning. You take x1 and condition on the sum and compare it to y1 conditioned the sum. I guess I kind of cheated slightly here, but like if you take x1, x2 and condition on x1 plus x2, this is the same as x1 condition on x1 plus x2. Because if you know x1, then, and you know x1 plus x2, then you know x2. So you can just leave x1 here. And so basically, and so what this means, the moral of this inequality is that if S of xy is at least eta times entropy of x and y, then you can construct some new pair of variables which also satisfy this. So let's say this is like x1, y1 plus x2, y2. So these are like my new pair of variables in both cases. So then you get from this that at least one of these pairs of variables just does at least as good as the original one. For some
Why it is with the xi, yi and not xy?
So I can be either 1 or 2. So basically, so we have this inequality on S's. So let me prove. So we know that S of xy, 2 times S of xy is at most so that's what we did up here. And we also know that entropy, 2 times entropy of xy is equal to entropy of x1 plus.
Oh, okay.
Yeah. So the second one is just a chain rule. Entropy of x tilde is entropy of the projection plus the entropy of the fiber. And so, yeah. And so if the ratio is at least eta for x and y, then it's at least eta for at least one of the two. One of the two guys. And so, so now, once we have this, we prove our theorem using induction on eta. So we start with something kind of small. So eta roughly 1/2 corresponds to PFR. So if eta is like 1/2 plus a little bit, then we can just use the PFR theorem as a black box. And then want eta to be kind of as small as possible. So And now there are three cases. So we start with where xy, the following three things can happen. So the subset has smaller doubling. So this means that S of x1 plus x2, 1 pi 1 plus y2 is at least some eta plus epsilon. Let me use a different letter here. Oops. That's the entropy. So basically the constant eta improved a little bit for that case. Then it can happen that the fiber has a smaller doubling. So S is kind of, if S is large, that means the doubling is small. So one conditioned on the sum. Entropy of that thing, and the last case, this is like near equality. So what if both of these inequalities are nearly sharp? Both inequalities. So kind of intuitively speaking, first two cases feel good because you're making progress. You got some two variables which have better additive structure, so you're kind of moving to the subspace, towards the subspace. And the third case seems tricky because what if you just get kind of the same parameters every time, so you're kind of stuck. And so the main thing which Green-Gowers, Manners, Tao did, they showed that this case 3 is actually okay. So they showed that 3 implies much better doubling. Basically, if you look at these kind of near equality cases and you kind of analyze them, how can it happen that it's near equality? Then you can extract kind of more information. And basically what they show is that x1 plus x2 is a small doubling in the sense that entropy of x1 plus x2 plus, okay, if I like double, if I take independent copies, that this is at most 1 plus c data. So basically, up to the precision of this like winning parameter, zeta of like how much we deviate from equality, you get small doubling. And so you can use PFR to find subspace. So here we got back to the like all like small doubling range where like k is small power. And so there is a subspace which interacts with our variable. And in their paper, so they were proving PFR, but they kind of did the same strategy, basically the quality of doubling in this third case was much better than the doubling that they were starting with. So this move makes progress in their argument. Okay. So in our setting, so there are for the other two cases, you still need to do something. So let's say we have case one. So the sum set has better doubling. So by induction, we can find a subspace V which interacts with x1 plus x2 and y1 plus y2. Where I mean that like some entropy drops, so like entropy of IV x1 plus x2 is kind of what's 10 minus something. And this basically is enough. So this kind of enough to conclude that x and y interact with B. So you need to like write some entropy inequalities, but this is sort of pretty easy to believe. You found some subspace which kind of captures the sum sets of your variables, so the variables themselves should also be captured. There's like slightly more going on, but that's roughly correct. And so the second case is a bit more interesting. So let me just explain it. So let's say that fiber has better doubling. So what does this mean? So we had these variables x1 conditioned on x1 plus x2 and y1 conditioned on y1 plus y2. So these are not actually variables. So in reality, we need to like sample v from 1 plus x2 and w from y2 and look at the variables x1 conditioned on x1 plus x2 equals v and y1 plus y2 equals w. And so by induction, so let's say that this is x sub v and this is y sub w. So by induction, x sub v, y sub w interact with some subspace v of vw. So basically, when I sample v and w, I get some variables.
I think it's better to use another letter for the subspace.
Sorry?
Maybe you can use another letter instead of V of VW, not to confuse things, right?
Like you want this to be u?
Not, oh yeah, that would be the best, I think.
Is this good? Okay. So basically, I have my variables x and y, and like fibers basically give you some pieces of x and y. And you know that these guys kind of interact with some subspace V of UW, but this is like, but it's not obvious that X and Y interacts with V of UW, because the fibers are like some small piece. Like,
So here it's the subspace itself, right? It's always different, potentially.
yeah, so
Yeah,
for each choice of U and W, you get some subspace. And it depends on U and W in some complicated way.
Yeah. So taking their union, something like that, is not good enough.
Well, there are too many choices of U and W. But so you are correct. So the idea, so let me tell you the idea. So the idea is to take a sum of a bunch of those. Yeah, that's gonna work. So you sample U from x1 plus x2, and I'll sample a bunch of W's. And these W's are gonna be all independent from each other. And let like Vk be V W1 plus V of U Wk. And K is like some large constant, depending on, your things. And so it turns out that this one works. So for large enough K, you can show that Vk is interacting with X. And yeah. And so this kind of completes the inductive step. So to show this, you need to write down like a bunch of entropy, which I don't think I'll be able to kind of explain fully. But that's roughly the idea. Okay. So that's basically kind of the sketch of the argument. So in the remaining undetermined amount of time, I can briefly mention some questions, like what kind of stronger results one can hope to prove. So some maybe open questions. So the first question is kind of pretty simple one. So our theorem gives the bound of L, which is of the order epsilon to the minus c, epsilon to the minus 1. So, and this doesn't match this Hamming ball construction. So can one get some 2 to the, can one get sharp bound? And this question actually has some motivation. So some 2 Red-Muller codes. So there is a paper about something about Red-Muller codes, which need this type of result as an input, and they pose this as a conjecture. Is there an exponential bound? But I don't know too much about this.
Because Cohen is working in codes, right?
So there is a paper with Marina Vizovska on Radmiller codes where they use like entropy additive combinatorics. It's let me see. It's the paper Polynomial Freiman-Ruger, Radmiller codes, and Shannon capacity by Abe, Sandan, Shashkov, Vizovska. So you can look it up. So let me just reiterate it. Okay, so another question which would be very nice to get is an energy version. So, so if you have set A, then energy of A is the number of A, B, C, D, and A to the 4, such that A plus B equals C plus D. That's kind of how many additive quadruples are there in the set A. And this is like slightly more analytic version of like counting how structured the set A is. So here's a question. Suppose I know that energy of A is at least 2 to the A to the 2 plus eta. So show that A intersect V is A is at least A plus epsilon for some V size at most A to the L.
And yeah, I guess 2 plus 8, the comment is you get 2 because you can always do A plus B equals A plus B. So you always...
Yeah, exactly. Yeah. And also, there is an easy inequality that E of A is at least A to the 4 over A plus A. So if you know that if A plus A is less than A to the 2 minus eta, then you get that energy is at least A to the 2 plus eta. So this is like weaker than doubling than A plus A. And basically, if for the small doubling, this is sort of standard. For the small doubling, it's basically equivalent that if like A plus A is less than K to a constant, is equivalent to energy being large. So basically, up to some pigeonholing, you can pass between these two conditions. So there is an equality in one direction, and then you can, if you have large energy, you can pigeonhole and find a subset of a small doubling. So for K, which is small power, this is sort of, there is nothing new, but for this regime, like you cannot convert between energy and subsets, so it's a new question, and I don't really know what to do with this one. Entropy doesn't play nice with energies, and yeah, it's a bit unclear. It's sort of equivalent way of saying, so you can phrase something in terms of entropy. Basically, it's the case when X and Y are dependent random variables. And small image doubling interact with subspace. So basically everything I was talking about was about independent random variables, and it was used in this fiber inequality in kind of important way. If you have a little bit of dependence, like small mutual information, then I think the argument should be okay, but I haven't checked carefully, but that wouldn't be surprising. But if there is some noticeable like dependence between variables, then that argument like just breaks down, and the statement is false. So like you cannot, like the statement of the theorem as I wrote it is false in that case. But it's like you cannot find the subspace such that the average intersection with the if the coset is large. So that's just false. But you still expect to find at least one subspace which intersect if each intersection is large. So you can kind of save the statement, but it becomes a bit more complicated. And that's morally equivalent to the energy version. And okay, and let me write one more question. So basically, kind of, we want some finer information below this a to the L. So finer subspace structure. So let's say you have A inside of V, and you already know that V is at most A to the L. And you know that A is at most e to the minus 2 eta, and it's also at most, let's say, V to the 1 minus eta. So A plus A kind of compresses a bit, and it doesn't fill out the whole space. Then there should be some intermediate space, subspace V prime inside of V, whose size is sort of not too large and not too small, which interacts with A. So, for example, like A intersect a translate is kind of sort of larger than expected. So yeah, so this is sort of there are several ways to phrase this question, but here you can just write some lower bound, which would be non-trivial. And you can be slightly more kind of ambitious here. So maybe 3 prime. Let me write it as 4 because it's kind of harder, but it's kind of related. So if you think of xy being again random variables on the space V, and these variables, and so like it's also the same kind of regime where V is not that much larger than x and y, and so like h of xy is at most minus eta h of xy and 1 minus eta V. So then there exists some V prime. Actually, what I want to say something stronger. Then x plus y should be close to a sum of independent random variables. So I want to like rewrite it as maybe z1, z2 where entropies of H of Zi are like intermediate. I don't know how to phrase this like completely precisely, but this is basically based on the examples that we have.
You mean close to independent random variables on V? Wait.
So Z1, Z2. So I want to say that like, for example, I can split coordinates in two parts, and like Z1 is supported here and Z2 is supported here. So so maybe I can split V as V1 plus V2, and so Zi is supported on Vi. Yeah. So somehow I can kind of split my variable in some sort of product type of structure. This is basically what happens in all examples. Example, if you have this union of cosets example, but this is like your A, then you have one variable which is where on the coset you are, and the other variable which is where inside of the coset, and the Hamming ball also has this kind of structure. So you can just split coordinates in two parts and take a set here, P n over 2, P n over 2 here. And so your variable is roughly the sum of those two. So that's kind of my intuition behind this. Like, I don't exactly know what it means to be roughly equal, because you can always mess up with a bit. So I don't know, but it feels like there should be something like this. And this would give you like smaller L type of control. You can smaller spaces which interact. Yeah.
Yeah.
Okay. So I think that's all I wanted to tell. Okay.
So yeah, you reached the upper bound.
Yeah. Well.
Yeah. Almost exactly.
Yeah. Yeah.
So are there any questions to Dima?
May you return to fiber inequality? Well, are you sure in sign? Because it looks like in the previous paper there was opposite sign in some very similar inequality.
So they use, yeah. So in their paper, they use Ruja distance. So they have like D of xy, at least D plus D. Basically, they have this different sign here. So like D of xy is h of x plus y minus 1/2 h of x plus h of y.
Okay, I see.
Yeah, so because of that, they have different direction.
If you
Thank you. It was a bit confusing. But
can you go down just 3 lines or 4 lines? So here I think it's clear this h of x plus y is just bigger than the two other h's at the end. Why the sign is like that? I think it's fine because kind of you want this h of px comma py in the second line, and then it would be equality, right? But it's bigger than us.
Yeah.
So yeah, it's fine, I think.
Yeah. Like You should think of it as like if S is large, then it means that there is lots of additive structure. So if X and Y have lots of additive structure, then either the projection or the fiber has lots of additive structure. So this kind of dictates what's the sign should be.
Yeah. Any other questions?
A bit more questions. In all entropy statements, there were two variables, x and y, and in conclusion, we get one set. Can we generalize it in sums a plus b? It's
yeah, you can have two sets.
so if you have two sets and the sum is
Smaller than
the biggest or so small to the
smaller than the product.
Then everything is generalized.
Yeah.
Okay. Thank you.
You can even have more sets. You could have like 3 sets whose sum is smaller than the product.
Any more questions? Okay, I think if not, then yeah, thanks a lot, Dima.
Yeah, welcome.